Hey, hi everyone. Welcome back to the Topos Institute Colloquium. Today, we're very pleased and honored to have Tom Leinster, and he's going to be talking about entropy and diversity, the axiomatic approach. Tom, whenever you're ready.
Thank you so much, Xiaowei. Thank you for the invitation. I'm excited to be giving this talk. I want to talk about a blend of different subjects. This talk is going to be moving around from category theory to geometry to a problem of mathematical ecology and back again. Because it's the Topos Institute, I'm going to lead with the notion of magnitude, which I'll explain what magnitude is, but it's a general concept of size that reaches into different parts of mathematics. And then after that, I'll talk about the very closely related subjects of entropy and diversity. So the plan is as follows. I'll start out with a really big picture summary of what magnitude is. And then I'll focus in on a particular case that's especially interesting, which is the notion of the magnitude of a metric space. It's some kind of invariant of size that has particularly interesting properties. And also it has an associated homology theory, which I'll very briefly mention. From there, I'll go into I'll do what seems like a complete change of gear, but in fact isn't, to talk about biodiversity. And then finally, coming back towards mathematics, I'll talk about maximizing diversity. So I have to explain what all these things mean, and I'll do so. So here we go. Here's the big picture description of magnitude. The idea behind all this is something extremely simple. It's a childish observation that for many types of mathematical objects, there is a canonical notion of size. So, for example, sets, and here I guess I principally mean finite sets, have cardinality, and it satisfies the inclusion-exclusion principle here, and it's multiplicative in this sense here. And then there's a similar pair of equations for volume, and let's say we're talking about volume of nice enough subsets of Euclidean space. Again, there's a kind of inclusion-exclusion principle, and the volume of a product is the product of the volumes. A little less obviously, Euler characteristic belongs to this family. And under certain hypotheses, Euler characteristic of topological spaces satisfies this same inclusion-exclusion property. So the kind of hypotheses I mean is, imagine that everything in sight is compact. And then also it is multiplicative in this sense. And in fact, this insight that Euler characteristic is the topological analog of cardinality came from Stephen Chanuel in the early 1990s. And it's well worth reading what he wrote about that. So there are these examples and others of invariants of size, cardinality-like invariants in mathematics. And so, of course, whenever you see in mathematics a bunch of things that behave similarly, the implicit challenge is to try to unify them into a single definition. And one answer to that challenge is a thing that I will explain to you, which is the notion of the magnitude of an enriched category. So enriched categories are a very, very general concept, more general than even ordinary categories. And there's a numerical invariant of enriched categories called magnitude that takes in these different examples in a sense that I'll talk about. So here we go with that. Before I get into the general abstractions, I need to give a very concrete and an explicit definition, which is kind of worth keeping in your head for most of this talk. So take a matrix. It doesn't have to be a square matrix. It can be over any ring you like. If the matrix is invertible, well, I guess it does have to be square. If it's invertible, then its magnitude is defined to be the sum of all the entries of the inverse matrix. So it's not at all clear why that should be an interesting thing to do, or why it should have anything to do with notions of size. But we'll see that it is, in fact, very closely related. I'll just make the little comments that if Z is not invertible, in fact, even if it's not square, you can actually extend this definition that I've just given you, but for the purposes of simplicity for this talk, I will just talk about invertible matrices. Okay, so the magnitude of a matrix is the sum of all the entries of its inverse matrix. Right, so there's a funny little definition that we'll come back to. I also need to talk about enriched categories. So I think this is quite a mixed audience, probably. Some people come from category theory, some people come from other directions. So I want to just give a summary of what enriched categories are. So first of all, a monoidal category is a category equipped with some kind of product. It could be called a tensor product, it could be a kind of Cartesian product, it could be something else. And when you have such a thing, a category enriched in V, it's like an ordinary category. So it's got a set of objects or a class of objects, but the things called hom AB are no longer sets, they're now objects of V. So the picture I have in my head is you've got the world of monoidal categories down here. So it's things like set with the Cartesian product or vector spaces with the tensor product. Here's another example. I have to explain this notation. So this is the two objects category. It's the ordered set consisting of 0 and 1, where 0 is less than 1. So we have an arrow from 0 to 1 and no other non-trivial arrows. And the tensor product is and, or minimum. So you think of 0 as false and 1 is true. And then, for example, 0 and 1 is 0, or the minimum of 0 and 1 is 0. And here's another monoidal category. It's the non-negative reals together with infinity. This is seen as an ordered set, and the monoidal structure is addition. Now, here's the big world of enriched categories. A category enriched in sets is just an ordinary category. So I've drawn that as a kind of fiber over the monoidal category of sets. A category enriched in vector spaces is what's sometimes called a linear category. So that means it's got a set of objects, but each of the things hom AB is not just a set, it's a vector space, and composition is bilinear. A category enriched in this funny little two-object category here turns out to be a poset, a partially ordered set. And as we'll see later, a category enriched in this monoidal category turns out to be something like a metric space. And I'll come back to that a little bit later. Okay, but if you haven't seen this kind of thing before, then the message is that the world of enriched categories is an extremely wide world. It includes categories and linear categories, ordered sets, metric spaces, and many things, many other things besides. Okay, so I said what the magnitude of a matrix is. I said what an enriched category is. And now I can tell you what the magnitude of an enriched category is. So here we are. Take a monoidal category V. And let's suppose we know how to measure the size of objects of V. So more specifically, I mean that we have a field K, and for each object of V, we have an element of K, a scalar. So the kind of examples to keep in mind are V is the category of finite sets, K is the field of rational numbers, and these bars mean cardinality, the cardinality of a finite set, which is a rational number, of course. Or it could be that V is finite dimensional vector spaces, K again is the rationals, and the bars mean dimension. So multiplicativity means, for example, the cardinality of a product is the product of cardinalities, the dimension of a tensor product is the product of the dimensions. So suppose you've got that stuff. From that, we get a notion of the size of a category enriched in V. So by the method I'm about to tell you, starting from a notion of the size of each object of V, we automatically get a notion of the size of a category enriched in V. So it goes like this. You write down the matrix. So it's a square matrix whose rows and columns are indexed by the objects of A. You write down the matrix whose entries are the sizes of the homs. So here we're working with categories that are finite, so only finitely many objects. And then you define the magnitude of the enriched category to be the magnitude of this associated matrix. So I'm making a couple of assumptions here. As I just said, I'm assuming that our category has only finitely many objects, and I'm assuming that this matrix is invertible. I mean, generically, a square matrix over a field is invertible, at least if the field is infinite. So the invertibility assumption isn't too strong. But we are assuming our categories are finite categories. Okay, so you take your matrix, you take your enriched category, you write down its matrix of sizes of Hom sets, you invert it, and then you add up all the entries. Now, it's absolutely unclear why this should be an interesting thing to do, and I have to persuade you that it is, right? But that's the definition, and in principle, it's something very simple. I said this was going to be a kind of big picture summary, and so I'm not going to go through details now. I'm just going to tell you some of the stuff that happens. And there'll be interesting stuff that happens when we're looking at metric spaces as enriched categories, but I'm going to talk about some other examples first. So first of all, ordinary finite categories. So that's a category with only finitely many objects, finitely many arrows. So here's a really important example. If you take the magnitude of a finite category, it is the Euler characteristic of the classifying space of that category. So to back up a bit, any small category has an associated topological space called its classifying space, or sometimes its nerve. With luck, that topological space has a well-defined Euler characteristic, and then these two things are equal. So starting from a category, either you can turn it into a topological space and take its Euler characteristic, or you can directly compute its magnitude. And these are the same thing. So it's a bit like the situation with group homology. If you have a group, you can realize it as a topological space and take its homology, or you can just directly take its homology combinatorially. So that links Euler characteristic into the picture. If you have a finite group, or any group, you can see it as a one object category. And then the magnitude of that category turns out to be the reciprocal of the order, which has long been known to be the morally correct definition of the Euler characteristic of a group. If you take a manifold with a finite triangulation, its simplices form a poset. A poset can be seen as a category, and the magnitude of that category is the Euler characteristic of the manifold. And an interesting extension of that result is to orbifolds, which I won't talk about at all. The interesting thing about orbifolds is that their Euler characteristic is not an integer. It's it's in general a rational number, but that's still equal to the magnitude. So the magnitude of a finite category is sometimes called the Euler characteristic of the category for exactly the reasons that I've just said. So all those examples are examples where we're looking at ordinary categories. So categories enriched in finite sets. Here's an example where we enrich in vector spaces. I guess I should have written finite dimensional vector spaces here, not just vect. Right, so this is something algebraic, which will make sense to the people it makes sense to. If you have an associative algebra that satisfies some finiteness conditions, you can, well, if you have any associative algebra, you can consider the linear category of indecomposable projective modules over it. And if the associative algebra is finite enough, then this linear category is also finite. There are only finitely many isomorphism classes of indecomposable projectives. And so you can try to compute its magnitude. What is that magnitude? Well, it turns out that it's something homologically sensible. It's a certain kind of Euler form that representation theorists recognize as something familiar is to do with the Cartan matrix of an associative algebra. So you get something recognizable in that algebraic situation too. So I'm not going to say anything more about that. The moral is just something that this general notion of magnitude recovers something algebraically known and sensible. So in fact, everything I've said so far, this general definition of magnitude is just recovering known things. Where it gets most interesting, where we go into the unknown or the new, is when we do consider metric spaces. So what's going on here? The first thing I have to explain is how a metric space can be regarded as an enriched category. Well, it's not too hard to see that the definition of metric space looks a bit like the definition of category. So a category has a collection of objects, a metric space has a collection of points. For any two objects in a category, you have a set, the set of maps from A to B, and in a metric space, you have a number, the distance from A to B. For any three objects in a category, you have a composition operation that looks like this. For any three objects in a metric space, you have an inequality that looks like this. And you can see a kind of resemblance between the composition and the inequality. And in fact, this is more than just an analogy. So 50 years ago, Lorvier wrote a very nice paper explaining how metric spaces are a special case of the concept of enriched category. So more specifically, there is this ordered set, which you can regard as a category. It has a monoidal structure given by addition, and a metric space is a category enriched in that ordered set. So I'm not going to spend time going into that. I'm just going to kind of fast forward to what the outcome of this observation is for us. So the next thing I want to explain is what the magnitude of a metric space is. So we just saw that metric spaces can be seen as enriched categories. We also saw that enriched categories have this numerical invariant of magnitude. And so we put those things together to get a numerical invariant of metric spaces called the magnitude. And let me just say it directly. So I'm now going to give a definition that involves no categorical terminology at all. It's just in explicit terms. So here's what it is. You take a metric space, and this is a finite metric space for now, and call its points A1 up to AN, put them in order. There is a matrix whose entries are not the distances, but the negative exponential of distances. I guess I should say where this negative exponential comes from. Back when I showed you the general definition of the magnitude of an enriched category, I said that we start from not only a monoidal category, but also a notion of the size of each object. And it's meant to be multiplicative. That multiplicativity here means that we need a function that takes as its input a distance and produces as its output an element of some field, and it should be multiplicative. But it's a little bit complicated to say out loud. What multiplicativity means in this particular instance is that this function should turn addition into multiplication. Taking exponential turns addition into multiplication, and it's more or less the only function that does, right? So e to the x plus y is e to the x times e to the y. So the reason why we get this exponential appearing here is because exponential is more or less the only function that turns addition into multiplication. So I said all that very quickly, and I guess it doesn't really matter if you don't understand it, but the message is that this transformation of distance is more or less the only thing that can be done here. Anyway, here's how you define the magnitude. You take your matrix, you take your space rather, you write down the matrix whose entries are e to the minus distances, you invert it, which you almost always can, and you add up all n squared entries of it, and that's the magnitude. So, you know, that's something very, very explicit and concrete. If I give you 10 points in the plane, you can go ahead and work out the magnitude of that 10-point space. So here are some examples. If the space has 0 points, the magnitude is 0. If it has 1 point, the magnitude is 1. Okay, so it's looking pretty much like cardinality so far. What if it has 2 points? Well, then it's something more interesting. So here's the recipe I just gave you. You take the matrix of negative exponentials of distances, you invert it, and then it turns out to be this, the graph of which looks like that. And the way I think about this graph is as follows. If your 2 points are very, very close together, so if L is nearly 0, then basically there's only 1 point. So, you know, if you're standing a long way away or if your eyesight is bad, you might think there's literally only 1 point. As they get further and further away, they acquire more and more distinct identities. They're more clearly different until when they're infinitely far apart, there are definitely 2 points. And that intuition is confirmed by this example. If you have a whole bunch of points and they're all distance infinity from each other, then the magnitude is just the cardinality. And the slogan is that magnitude is the effective number of points. There are effectively 1 and a bit points here, 1.1, 1.2, 1.3, and so on until you've got 2 points there. It's very important for metric spaces that you can scale them. So, you know, anyone, I mean, from a geometric point of view, that's obvious. You want to be able to change from, you know, inches to centimeters or whatever. And from a categorical point of view, you have an automorphism of the base monoidal category V for every real number. So what this means is that the magnitude of a metric space isn't really just a number, but it's a function. Because whenever you have a positive scale factor t, you can scale your metric space by a factor of t and then take its magnitude. And so we get this whole function, or at least partial function, like this. So for example, we just saw that the magnitude function of this 2-point space was this. So that's how the magnitude changes as you scale the space up and down. And it's not too hard to show that when you have a finite metric space, it's only got finitely many singularities. So there might be a few, just a finite number of points where scale factors where it's undefined, but then thereafter, it's always defined. And in fact, there are no singularities if you're a subspace of Euclidean space. And moreover, after a certain point, as you might imagine, as you scale up, the magnitude increases. And at infinity, as you go towards infinity, the magnitude is just the cardinality, which again reflects the size-like nature of magnitude. It's also a first hint of something that we'll keep seeing later on, that the asymptotic behavior of the magnitude function as you go towards infinity is extremely interesting, and you recover invariance from it. So that's all very well. But at the moment, we're just talking about finite spaces, and finite spaces are, well, they're interesting. I mean, they're interesting in data science, for example, but most of geometry is not about finite spaces. So let's see if we can take this definition and extend it further. And the natural point of call, first point of call anyway, is compact metric spaces. And probably, you know, if everyone listening to this talk tried to write down a definition of the magnitude of a compact metric space, there might be, like, you know, a few different proposals, 3 or 4 or 5 different proposals, and you can ask whether they give the same result. And it was shown by Mark Meckes a while ago that basically all sensible ways that you might think of doing it give the same result, at least under a certain technical condition, if your space is positive definite. And the proof involves some functional analysis that I won't go into. I won't give the definition of positive definite. I'll just say that it's quite a mild condition. It includes all subspaces of Euclidean space and many other things besides. The simplest way of saying what the definition for a compact metric space is this. the magnitude of a compact positive definite space is the supremum of the magnitudes of the finite subsets. Okay, so now in principle, you could go ahead and compute the magnitude of a disk, for example, except it turns out to be really difficult. Let me say how this invariant behaves. So the first, I think, nice result is that the magnitude of a straight line is a linear function. So it's got a degree 0 part, which you should view as being the Euler characteristic of the line segment. And it's got a degree 1 part, which up to a scale factor of 1/2 is the length of the line segment. A similar two-dimensional result, and this is with the L1 or taxicab metric on your rectangle, is that the magnitude function is, well, this is just 1, but morally it's the Euler characteristic. The degree 1 part, the coefficient of t to the 1, is the perimeter up to a known scale factor, and the degree 2 part is the area up to a known scale factor. And you'll notice also in both these cases, the degree of the polynomial involved is the dimension of the space. And this leads on to some much more general results, which really confirm that the magnitude of a metric space is something like an invariant of size, that magnitude, and especially its asymptotic behavior for large scale factors, encodes geometric information. So here's a result, again by Mark Mekas. If you take a compact subset of Euclidean space, then from the magnitude function, you can recover its Minkowski dimension. So Minkowski dimension is one of these notions of fractal dimension, like Hausdorff dimension, but a little different. And actually, the way you recover it is it's the growth of the function. So for example, if the magnitude function is a polynomial, its Minkowski dimension, sorry, the dimension of the space is the degree of the polynomial. And this uses some potential analysis and the notion of maximum diversity that we will come to. A result by Simon Willerton says a bit, well, it says something different. It's about homogeneous Riemannian manifolds. Then the asymptotic behavior of the magnitude function recovers the volume, and it also recovers the total scalar curvature of the space. So more geometric invariants. And this uses a different kind of analysis. Here's a really important one shown by Juan Antonio Barceló and Tony Carberry, that I should have said A here is meant to be a compact subset of Rn. You can recover from the magnitude function the volume of the space, and that uses some PDE stuff. They also showed a non-asymptotic result, which is that the magnitude function of an odd dimensional ball, it's only true for odd dimensional balls, it's very strange, is a rational function. So in other words, the magnitude of a ball is a rational function, the ratio of two polynomials in the radius. And so the first few dimensions look like this. This one we've seen. The three-dimensional ball, the magnitude function is a polynomial, but a five-dimensional ball, it's not. And so, I mean, there are very mysterious things about these rational functions. Simon Willerton has done some work on what the coefficients mean, but you can see that there is something special about the magnitude of a five-dimensional ball of radius -3, whatever that means. The analysis here gets more and more serious, and I think the following result is probably the most analytically sophisticated of all of them. It's way beyond me. So there's a recent result of Heiko Gimperlein, Magnus Gofeng, and Nicoletta Luca, which says that if you have a nice enough subset of Euclidean space, then from its magnitude function, again, the asymptotics at large scale, you can recover the surface area, the n-1 dimensional surface area of the space. And that uses some stuff related to the heat equation proof of the Atiyah-Singer index theorem. And it's really crucial here that the scale factor T is seen as a complex parameter. Even though it makes no sense to scale a space by a complex number, you nevertheless need to do that, apparently. Another part of that same work is something that's that again brings us back to this idea that magnitude is an invariant of size. So it doesn't literally satisfy inclusion-exclusion. So if it did, then the magnitude of a finite space would just be the cardinality. But it asymptotically does in this sense here. Okay. So that's all I'm going to say about the magnitude of metric spaces. But you can see that it's there's a whole wealth of geometric invariants that are hiding inside magnitude, and there's a lot we don't understand yet. Instead of saying more, I'm going to talk very briefly about the associated homology theory called magnitude homology. So the idea is that we want to categorify magnitude. In other words, find a homology theory of enriched categories whose Euler characteristic is magnitude. And the first context this was done in was the context of graphs, which you can see as, so you can see any graph as a metric space. You say that the distance from one vertex to the other is the shortest path length. So a graph is a special metric space, which in turn is a special enriched category. And Richard Hepworth and Simon Willerton defined this graded homology theory. So it's not only got a homological degree n, it's also got a length scale L. And if you take the Euler characteristic, there's one Euler characteristic for each L. You can compile them all in a kind of generating function. And that generating function turns out to be the same thing as the magnitude function. So the Euler characteristic of this graded homology theory is magnitude. If you know about the story of the Jones polynomial and Khovanov homology of knots, then you should think of it as being in the same spirit. So they did this, and then the implicit challenge was to extend their definition to enriched categories, which Mike Schulman and I did some years later. And I won't say what the definition is. I'll just say a little bit about how it works for homology, for metric spaces. And in that case, it's a homology theory with a real grading. And again, it categorifies magnitude. So you have to be a bit careful about what that means. This is an uncountable sum in principle. But you get a similar result. Geometrically, there's a lot that's interesting about the magnitude homology of metric spaces. So for example, it detects convexity. It's genuinely a metric homology theory and not just topological. Even first homology detects convexity. And then a really nice realization by Kaneta and Yoshinaga was that topological homology, of course, detects whether holes exist, but magnitude homology measures how big the holes are. And they have some precise results expressing that. Incidentally, this talk about homology of metric spaces may be making you think about persistent homology, which is another homology theory of metric spaces, also with a length scale. And so there have been a couple of investigations of the relationship, first by Nina Otter and then by Simon Cho. And so magnitude homology and persistent homology are related, but they're quite different. They detect quite different information about a space. So it's interesting to compare and contrast those theories. Okay, but that's all I'm going to say about homology theory. And I'm now going to turn to diversity. What does the word diversity mean? You can think about diversity in many contexts, biodiversity, diversity along various social axes as well. I'm going to talk about biodiversity, if nothing else, as a simple way of speaking, but you can try and reinterpret it for other kinds of diversity too. So a conceptual question that's been bothering ecologists, concerning ecologists for a good 70 years is that if you have an ecological community divided into species, what are the most reasonable ways of quantifying its diversity? So the very simplest answer, the most common answer, is you simply count the number of species present. That's very crude, and it doesn't pay any attention to which species are more or less abundant. It might be that almost all the species are near extinction, in which case it's not very diverse, or it could be there's a healthy balance. So a more sensitive answer is to use the abundance distribution of species, and I mean relative abundance. The sum of these PIs is 1. This is a probability distribution. And I'm just going to put this formula here without explaining where it comes from, but there's a very useful family of diversity measures that's defined like this. So this formula doesn't make sense if Q is 1 or Q is infinity. You take the limit in Q, which does exist, and that's how you handle those cases. So, for example, if you have the uniform distribution, all species are equally abundant, then the output here is N. It's easy to see. So the diversity of a species of a community of N equally abundant species is N. So in ecology, dq of p is called the Hill number of order Q. In information theory, it's called the exponential of the Renyi entropy of order Q. And especially interesting is the case Q equals 1, which is the Shannon entropy. I'm not going to use the word entropy very much in the rest of this talk, but everything I say about diversity, you can put a log in front of it and you get entropy. So log of the Hill number is the Renyi entropy, and so on. But entropy and diversity are very, very closely related. It's just almost a way of speaking, but also a way of looking at things. I have to say what this parameter Q is doing, right? Because I've got one diversity measure here for each value of this real parameter Q. So what does it do? So here's an example. There are 8 species of great ape on this planet. So there's us, there's 3 species of orangutan, 2 species of gorilla, chimpanzees, and bonobos. So the frequency distribution of the 8 species of great ape is extremely, well, extreme, because if you take 10,000 representative great apes, only one of them is not human. So we've successfully outcompeted or killed all the other 7 species. And so only 1 in 10,000 is not human. That last one is shared between the other 7 species. This is what the diversities look like, with Q on the horizontal axis and the diversity on the vertical axis. And so it's a very it's very steep at the left-hand end. It looks like it's 1 for almost all values of Q. So this is very, very, very slightly above 1. But the fact that it looks like 1 for most values of Q is reflecting that there is essentially only 1 species of great ape on the planet, us, and the others are incredibly rare. The fact that it's 8 at Q equals 0 is because there are 8 species present. And the fact it's so steep here is because the distribution is so extreme. If you take a fantasy distribution where there are only 2 species, let's say chimpanzees and bonobos, and they're equally abundant, then the graph looks like this. Whatever Q is, there's always, the diversity always comes out as 2. And you'll notice that these graphs cross, which is because from most viewpoints, most values of Q, this fantasy distribution would be more diverse than the real distribution. It's only if you look at low values of Q, which prioritize rare species, that our actual real world distribution seems more diverse. So in brief, it doesn't really make sense to ask whether one distribution has higher diversity than the other, because the answer depends on Q. All right. The title of this talk was Entropy and Diversity, the Axiomatic Approach. So let me explain what the axiomatic approach means to me. You can ask, what is so special about these Hill numbers? I just gave you a formula. I didn't motivate why it's a sensible definition. There are loads and loads, dozens, maybe hundreds of other diversity measures that have been proposed in the literature. So why not use one of them? The axiomatic approach is to say, well, what properties do we want of a diversity measure? What is sensible, logical behavior of a diversity measure? And can we identify exactly those diversity measures that have those sensible properties? So here's a theorem. Let's take a function that assigns a real number to any finite probability distribution. If it satisfies 7 desirable properties, which I'm not going to go into, then it must be one of the Hill numbers. So you can prove theorems along those lines. And so in this sense, the Hill numbers are the only sensible diversity measures. It's quite hard to prove theorems of this type, but it resolves, in some sense, the question of which diversity measures should you use. Okay. They're the only sensible diversity measures for this very simple model of a community. And that's this is something very important, because I've said nothing at all about the fact that different species are differently similar to each other. So imagine in these two pictures that the first field consists of 20 rather similar species of grass. You can barely see the difference, but the lower one consists of 20 very different plant species. So diversity should reflect that. I mean, that's what people mean by the word diversity. It should reflect the difference between the species, not just how abundant they are. And we want to incorporate that biological reality. And the Hill numbers really, they're very crude in that they only look at species abundances. In fact, I mean, in the ecological literature, almost all diversity measures ignore this aspect of the varying similarity between species, which makes them very crude. So let's say we have some way of quantifying the similarity between any two species. And think of it as on a scale of 0 to 1, with 0 meaning that two species have nothing in common, nothing whatsoever, and 1 meaning they're identical. So this gives us an n by n matrix, which I'll call Z, an n by n matrix of similarities. And you can measure similarity really however you want. The absolutely most naive, crudest thing to do is to say that identical species are identical and different species have nothing whatsoever in common. So that seems like a really extreme assumption, but that's a thing that you can do. So then Z is the identity matrix. Slightly less crudely, you can just look at the taxonomy. So you say the similarity is 1 if the species are identical. It's a half if your species aren't the same, but they're in the same genus. And it's 0 otherwise. And of course, you can make up variants of this, taking into account other levels of taxonomy or having different numbers here. And then you can try and do it genetically, like we are 96% genetically identical to orangutans, for example, that kind of thing, or by other means as well. On a more mathematical, from a more mathematical point of view, what you might do is start with a metric space. If you have a metric on the set of species, then a sensible thing to do is define the similarity to be the negative exponential of the distance. So the smaller the distance is, the more similar the species are. Okay, so from there you can look at. So once you've got this matrix Z, you can look at to define diversity measures that take similarity into account. So we have our community, we have our vector of relative abundances, and we have our matrix of similarities. And I'm just going to write down what the formula is without justifying it. So the diversity of order Q is this. So that ZP in the middle is the matrix Z times the column vector P, and ZPI is its ith entry. It doesn't matter. We're not going to use this formula, so I'm just putting it in front of you to show you what it looks like, that's all. And I will tell you what the exceptional values of Q look like in this case. They look like this. But again, it doesn't really matter. It's just, yeah, these are just formulas. And so what matters is not the formulas. You can motivate the formulas, but I've just chosen not to. What matters is is what they do, not what they are. And what they do is unify a whole bunch of diversity measures that exist in the ecological literature and other branches of science too, economics and others. So this extreme case where you take the naive model, you say two different species never have anything at all in common, which seems crazily extreme. Actually, this is what recovers the Hill numbers, which in turn unify most of the measures in the literature. And as a very special case of that, you get Shannon entropy, or sorry, the exponential of Shannon entropy. Taking an arbitrary similarity matrix and taking Q equals 2, you get something that essentially is known as Rao's quadratic entropy. So it's kind of appealing. It's the reciprocal of the mean similarity between individuals. So, right, imagine you've got your community and you choose two individuals at random, and typically they're very similar. Well, that would mean that your community is undiverse. So the denominator here is very large, and therefore the actual thing itself, the diversity, is small. So that's a sensible measure of diversity. Okay, so now I'm going to swing back towards the more mathematical end of things and talk about how an analyst might look at all this. So we assumed, of course, that the set of species was finite. But you can actually do a version of all this, of the definitions that I've been showing you, not on a finite set, but on a compact Hausdorff space. So then the thing that I've been calling P, a probability distribution, becomes a probability measure, which I'll now call mu. And the matrix that I was calling Z now becomes, well, now it's more natural to write it like this and call it a kernel. And so if you've got a compact Hausdorff space, a Z like this, satisfying a couple of conditions, and a probability measure, you can define these diversity measures. In particular, if you have a compact metric space, then a natural thing to take for your similarity kernel is the negative exponential of the distances. So when you do that, the formulas I showed you before, the sums become integrals. Essentially, that's all that's going on, and the notation changes ever so slightly. I've written here joint work with Emily Roth because actually, even showing that these definitions make sense, showing that that things are well defined is not so easy. But I'll say more about that joint work in a second. So anyway, again, the formulas don't matter. I'm just waving them in front of you. But the fact is that you can do this. And so this takes on a geometric life of its own. And the way to think about diversity measures in this kind of situation is as follows. Take a compact metric space, take a probability measure on it, and think of it as kind of a, piles of sand or whatever. Then it's a measure of how spread out that sand is. I always think about the fact that when you move into a new apartment, maybe all your boxes, all your belongings are piled up in corners of the rooms. And then as you unpack, you gradually spread your belongings out across the apartment. And so these diversity measures would increase as you did that because it's spreading out the measure. So the last thing I want to talk about is maximizing diversity, and this will just be a short section. And this has ecological interest, but also mathematical interest. So here's a question. Let's suppose we fix a compact Hausdorff space and a kernel. So for example, we might have 10 kinds of plant seed, and we're going to plant our garden. And the question is, in what proportion should we plant those 10 types of seed in order to maximize the diversity? Or generally, which probability measure should we put on our space in order to that spreads things out as much as possible? And the answer is not usually the uniform distribution, because this is a space with some structure, with a non-trivial metric on it. Now, in principle, this question has no answer. And the question also of what the maximum value is has no answer. Because remember, you've got these different Qs. You've got this parameter Q. And remember, you had those, I showed you the graph with the crossing, with the two crossing curves. And it said that, so the lesson there was that taking different values of Q changes which things seem more diverse than other things. So we've got no right to expect that this answer should be independent of Q. But it's a theorem that the answer to both questions is independent of Q. So in other words, there is some probability measure that maximizes all these infinitely many diversity measures at once. Again, that is not usually the uniform distribution, even in the case of a finite set, because the similarity matrix introduces some non-symmetry. Moreover, the value of the maximum diversity is independent of Q. So there's a single maximum diversity that doesn't depend on the viewpoint chosen. I mean, there are interesting things to say about that from the ecological point of view, but from a geometric point of view, that means that whenever you choose a compact metric space, a disk or something, there is a canonical probability measure on it, which is the maximum diversity measure. And there's a canonical real number associated with your compact metric space, which is the maximum diversity. And that doesn't depend on a choice of parameter Q. It just is, so the Euclidean disk of radius 4 has a certain maximum diversity. That's just a number. So the very last slide just says a little bit about this maximum diversity, which is that it's very closely related to magnitude. And that's how the two concepts of diversity and magnitude fit together. So for any compact metric space, the maximum diversity is not equal to the magnitude, but the maximum diversity is equal to the magnitude of some closed subset. And again, maximum diversity as a geometric invariant encodes lots of geometric information. And again, you look at the asymptotic behavior for large T. So maximum diversity and magnitude are very closely related. As for magnitude, the growth rate of maximum diversity is the Minkowski dimension. And as for magnitude, you can recover the volume of a subset of Euclidean space from its maximum diversity, or more exactly from its maximum diversity function. And you do it like this. But there's a whole heap that we don't know about maximum diversity. So we don't know what the maximum diversity of a Euclidean disk of radius 4 is, or indeed of any Euclidean ball of any dimension bigger than 1. No one knows what the maximum diversity is. So there are some very, very basic things we don't know. There's a whole lot we don't know. There are many mathematical mysteries. There are many open questions. Okay, so that's pretty much all I want to say. I've told you about magnitude. I've told you about maximum diversity. And then in this very last slide, I've told you about how they fit together. If you want to read more about this, then there's at least a little bit on everything I've said in this book. There's also a bibliography I've been maintaining of all the works I know about on magnitude, which overlaps a little bit with stuff on these diversity measures. But that's it. Thank you very much for your attention.
Thank you, Tom. Thank you so much. Thank you for bringing us on that journey into the math and then into biology and back to the math. And that was a very interesting account of magnitude and diversity. Thank you so much. So we have time for questions. And the way we do this in the colloquium is that if you're on the Zoom chat, you can raise your hand and I will call on you to unmute yourself. Or you can type your question in the chat and I will ask you on your behalf. Okay, so I see Valeria, your hand is up. So perhaps you can go first.
Hi, Tom. Thanks so much. That was really very impressive.
Thank you.
I mean, I'm sorry, I kind of wanted to hear that because I wanted to think about connections between mathematicians and activists, right? So, I mean, so my question is definitely in the direction of what can we tell the ecologists about? I mean, so let me say, be stupid directly and say that, you know, the thing is, if what we want to choose, I mean, there's a very huge difference between having a huge diversity of insects and nothing else on the planet, right? Or only cockroaches or something like that. So the question I have is that, how do we kind of think, how can we make some inroads into thinking about the things that are happening in the metric space, the metric of similarity that we are putting into metric spaces, and what happens in real life? Have you been thinking along those lines too?
Right. So the question of choosing similarity is a different one. Is a difficult one. So choosing, so deciding on the similarity between species, and it's not at all clear what you should do. You know, one lesson is that, for example, if you take a genetic measure of similarity, there's no reason then you're going to get a genetic measure of diversity, and genetic diversity might be different from phylogenetic diversity, which might be different from functional diversity. And so there's never going to be an answer to, you know, like, what is the one true diversity? There are then questions about things like value. So we might value some insects more than others. We might not value insects very much at all, or we might value them a lot. And that's not built into the measures I've talked about, although there is some stuff in this in my book about trying to incorporate value. So people have looked at that. People have looked at people talk a lot about ecosystem services and what which is basically, you know, what organisms and communities are of value to us. So yeah, I think we're really in the early days of figuring these things out mathematically.
But may I kind of just confirm what I think I heard, but I'm not so sure. I mean, you did say that all the ecologist measures are just subcases of the Hill number, didn't you? Or have
I might have said all, but if I said all, I should have said most.
Right.
So.
And because it's obvious that people kind of not coming from mathematics would try to think just about number of species, right? It's a very obvious thing to think, but you know, I would hoped that they would have done something a little bit more sophisticated than that.
Yeah, so they have. I mean, so if you actually look at papers written by ecologists, not mathematicians, then the diversity measures that you see most often are number of species, Shannon entropy, and the Q equals 2 one, which is a quadratic form. It's to do with the probability that two random individuals are from the same species. Mm-hmm. Those are the ones you see most often. Now and again, you see the thing that I mentioned as Rao's quadratic entropy, which does include species similarity, but the introduction of species similarity into diversity measures is, you know, it's relatively new and relatively little taken up, which is strange given how crude it is not to include it.
Yeah. Well, thank you. That's very, very thought-provoking, the talk altogether. Yeah, very good. Thank you.
Thank you, Valeria and Tom. Next, I think we have Andrea Blas. You can lower your hand. Sorry, you can unmute yourself.
Not sure. Okay, I am unmuted. Let me see if I can even lower my hand. No, it's still allowed to raise my hand.
Don't worry about that.
So I want to ask some category theory type questions. Beginning with, is it reasonable to expect, or is it proved, that the magnitude of a category is an invariant with respect to equivalence of categories?
Right. So I worked under this assumption that matrices of cardinalities are invertible. So if you have two isomorphic objects, then two rows and two columns of the matrix are going to be identical, so it's not going to be invertible. So the definition I gave, you know, you couldn't have two equivalent categories where these are both invertible. But yeah, when I alluded to a generalization of this definition that doesn't require the matrices to be invertible, and under that generalization, yes, equivalent categories have the same magnitude.
Okay. So let me push that idea a little further. Is there any, suppose I have a pair of adjoint functors between two nice finite skeletal categories. Can I say anything about their behavior relative to the magnitudes?
Yes, the magnitudes are the same, which is a cousin of the fact that homotopy equivalent spaces have the same Euler characteristic.
Okay, good.
So
Okay,
that tells you that tells you, for example, that if a category has an initial or terminal object, then its Euler characteristic is 1, its magnitude is 1.
Okay. Well, yeah. Thank you, Tom, and thank you, Andreas, for the question. So Andrew, your hand is up. Please feel free to unmute yourself.
Yeah. So just a quick question. You mentioned near the start of the talk that the magnitude is equivalent to Euler characteristic of the classifying space of a category.
Yeah.
This would apply to not finite categories in general. Is this sometimes an easier way to calculate the magnitude of non-finite categories, or can you not do this?
Well, so in order, yeah, so the magnitude of a non-finite category is undefined. So actually, so the mild conditions here are kind of further finiteness conditions. You might think that finiteness of a category is as finite as you can get, but actually it's not, because you might have kind of loops. In order for the classifying space to have a well-defined Euler characteristic, you need to insist on something like there are only finitely many non-degenerate simplices in the nerve. So actually, it's usually you get a wider degree of generality by working with the direct combinatorial definition than by trying to go into topological spaces. Nevertheless, so if you decided to define the magnitude of a category as the Euler characteristic of its classifying space, that would probably be a more restrictive definition than the one I've given.
Okay, thank you.
Thank you, Andrew, and thanks for your question. I'm sorry, I'm seeing a very long list of questions, but I think it seems like the sender wants to email this to you after the talk. So I have a question. So you were talking about Rao's quadratic diversity,
yeah,
the one with the matrix Z,
yeah,
and you're talking about how that kind of measures the diversity when you have a spread of things in a room. And that kind of reminds me a little bit of optimal transport. What's the sign? Is there some relationship there that we know about?
I'm not sure. So I've mentioned a few times the work of Mark Mekas on this. So when he did stuff involving maximum diversity, he was using Q equals 2, like here. And he was using the Wasserstein distance, which is, I know, comes up in optimal transport as well. And but that's the only kind of connection that I know about. Of course, there might be connections that I have no idea about.
I see. Yeah, that was very useful. Yeah, so we can use the Wasserstein distance as the Z matrix in here, for instance. Okay. Sorry, I'm looking at the questions in the chat. Sorry if I seem distracted. So I have another question myself, which is that, I think in one of your slides, you're defining entropy or diversity as the integral of the Euler characteristic times e to the minus LT dl. Yeah, the sum of that. And it looks like a Laplace transform of the Euler characteristic.
Wait, sorry, do you mean like here or no?
Sorry, it's like the sum of Euler characteristics of A with e to the minus LT. I don't remember what slide number was that.
Oh yeah. So was it the stuff about homology?
Yes, I think so. Yeah.
Right. Yeah.
So yeah,
Like,
exactly. This thing here. So that looks like a Laplace transform of some kind, and I mean, I worked more with statistics in the past, and we know that you can also do the Fourier transform where you have the complex, you have it in the exponent instead of just t, and sometimes those Fourier transforms have much nicer properties. I'm wondering if there is, you talk about complexifying the t. In this case, are there similar kinds of functions over t, where you're looking at these of, like, instead of using the exponential of LT, you're using some e to the ILT, and have you looked at functions like that, or are they interesting?
No. So people have mentioned that the formal resemblance of this formula with the Laplace transform before, but I think, I mean, what you just said, that the magnitude function seems to be something like the Laplace transform of the Euler characteristic. I never quite thought of it in those terms, and that's very provocative thought. Yeah, I suspect there's something there, but I have no idea what it is. Oh, thank you for that.
I see. Yeah, I'll be interested to hear if there's a relationship. Yeah, thank you, Tom. So
Oh, I think either Xiao is still reading. I can't hear anything.
Yeah, I think he's muted.
I'm
Yeah.
sorry. I was muted. Yeah, sorry. I was saying that there's a long list of questions here, but I'm going to send it to you by email.
Okay.
Yeah, but
okay,
we have a question on YouTube, which I think is some question on YouTube, which I think is very interesting. I'm going to ask. I'm sorry. Give me a moment. I need to find my YouTube. Yeah, here's the question. So how does the concept of measure from measure theory and enriched category magnitudes compare, especially with given what you showed? Sorry, I'm trying to understand the question here. How do you, how does the idea of magnitude that you've talked about compare with the idea of measure from measure theory, especially given the fact that you talked about areas and lengths and things like that being derived completely from magnitude?
Yeah, well, I guess that is the connection that I see, that there's like let's just go back to some of the relevant slides. So this result of Barceló and Carberry tells us that the magnitude function of a subset of Rn determines the volume, and then there's a similar result for surface area here. And so I suppose that's the connection I see, that it's not that volume is literally a special case of magnitude, but but the magnitude function knows the volume. It knows the dimension of a space, the Minkowski dimension of a space. It knows the volume. It knows the surface area, and so on. So that's the sense in which it generalizes. So I'm not saying that's the only kind of thing you could look for. You could ask for other results, but that's the connection that I see.
I see, and magnitude is by itself not a measure, right? There's no way to think of it as a measure on a space.
No, it's it has some measure-like properties. This is a measure-like property that this inclusion-exclusion formula, but it's not literally a measure. No.
Okay. Thank you, Tom. Well, I think those are most of the questions, and let us thank Tom again for such an interesting talk, and thank you for the discussion. And I'm going to end the live stream now, and we're gonna have a continue on the Zoom chat.
Yeah, well, thank you so much.